At 5:30 in the morning on December 16th, 1944, a young engineer named Harry Diamond stood in a frozen bunker near Monschau, Germany, watching something impossible unfold before his eyes. German infantry were being cut down by artillery shells that exploded precisely 30 feet above their heads, raining shrapnel down into positions where soldiers believed themselves safe. What those dying men didn't know was that they were being killed by a device their own scientists had spent a decade trying to build and had ultimately declared impossible to create. The weapon tearing through their ranks contained technology so revolutionary that it had been classified at the same level as the atomic bomb. And the man who had solved the engineering puzzle that made it possible had learned electronics not in a prestigious university laboratory, but in a farmhouse workshop in rural America, wiring crystal radio sets by kerosene lamplight. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Harry Diamond was born on February 18, 1896, in the small town of Russia, Estonia, then part of the Russian Empire. His family immigrated to the United States when he was 2 years old, settling in a modest farm community outside Washington, where his father worked as a laborer and tried to scratch out a living from unforgiving soil. The Diamonds had no money for formal education beyond elementary school. Harry's future seemed predetermined. He would work the land like his father, marry young, raise children in poverty, and die without ever travelling more than 50 miles from where he was born. But Harry Diamond possessed something that couldn't be taught in any classroom and couldn't be purchased with any amount of wealth. He had an intuitive understanding of how electricity worked, a gift so profound that by age 12 he was building functioning radio receivers from scavenged copper wire, bottle caps, and crystals he extracted from broken phonograph components. The farm boy who would one day revolutionize warfare spent his teenage years in a workshop he'd constructed in his family's barn, teaching himself electromagnetic theory by reading technical journals he borrowed from the local library. He couldn't afford new components, so he learned to salvage vacuum tubes from broken radios, rewind transformer coils by hand, and fabricate capacitors from waxed paper and aluminum foil. When other boys his age were playing baseball or chasing girls, Harry Diamond was conducting experiments with radio frequency circuits, documenting his findings in careful handwriting in notebooks he made from scrap paper. His neighbours thought he was odd. His family worried he was wasting time on foolish dreams. But Harry Diamond was developing skills that would one day save thousands of lives and change the course of history. In 1914, when Harry was 18 years old, World War I erupted in Europe. He watched from rural America as nations hurled millions of men into industrialized slaughter, and he understood with clarity that future wars would be won not by the bravest soldiers or the most brilliant generals, but by whichever side could harness technology most effectively. He began focusing his self-education on military applications of radio technology, particularly on the problem of detecting aircraft. Even then, aviation was transforming warfare. Airplanes could cross enemy lines, photograph troop movements, and drop bombs on targets that had previously been unreachable. The nation that could develop reliable methods of detecting and destroying aircraft would possess an overwhelming advantage. Harry Diamond decided that would be his contribution to the world. By 1920, Harry Diamond had managed to secure a position as a junior technician at the National Bureau of Standards in Washington. He had no college degree, no formal credentials, and no connections in the scientific establishment. What he had was a portfolio of working radio equipment he'd designed and built himself, and a demonstration of technical knowledge that impressed the Bureau's chief engineer enough to take a chance on an uneducated farm boy. Diamond started at the bottom, cleaning equipment and running errands for senior researchers. But he watched everything, learned everything, and asked questions that revealed a mind capable of intuitive leaps that formerly trained engineers often missed. Within 2 years, he was leading his own research projects. Within 5 years, he held patents on radio direction finding equipment that the Navy was using operationally. Diamond's breakthrough came from a problem that had frustrated researchers for years. Radio signals could be used to detect distant objects by measuring reflected electromagnetic waves, a principle that would eventually be called radar. But existing equipment was enormous, fragile, and required skilled technicians to operate. Diamond understood that military equipment needed to be simple enough for ordinary soldiers to use, rugged enough to survive combat conditions, and compact enough to deploy rapidly. He began working on miniaturization techniques that would allow complex radio circuits to be packed into smaller and smaller spaces. His colleagues at the Bureau of Standards thought he was chasing an impossible dream. Radio equipment required large vacuum tubes, heavy transformers, and bulky power supplies. The laws of physics seemed to impose hard limits on how small these components could be made. But Harry Diamond had learned something in his farm workshop that university-trained engineers often missed. The laws of physics don't change, but the engineering solutions to specific problems are limited only by imagination and persistence. If large vacuum tubes couldn't survive mechanical stress, perhaps tiny vacuum tubes could be designed differently to withstand forces that would shatter conventional components. If heavy transformers were too bulky, perhaps circuit designs could be modified to operate with smaller transformers or eliminate them entirely. Diamond began experimenting with miniature components, testing them to destruction, analyzing the failure modes, and redesigning them to address each weakness. He worked methodically, documenting every failure and every success, building a knowledge base that no one else possessed. By 1935, Diamond had developed radio direction finding equipment small enough to fit in a backpack and rugged enough to survive being dropped from a moving truck. The Army Signal Corps began using his designs operationally, but Diamond was already thinking about the next challenge. Aircraft were getting faster and flying higher. Anti-aircraft guns were becoming more powerful but less accurate. Gunners needed some way to detonate shells at precise altitudes, near fast-moving targets. Mechanical time fuses required gunners to estimate the target's altitude, calculate the shell's flight time, and set the fuse manually before loading. Under combat conditions, with aircraft maneuvering at high speed, these calculations were nearly impossible to perform accurately. Most anti-aircraft shells exploded harmlessly in empty sky, wasting ammunition and leaving attacking aircraft untouched. Diamond understood that the solution required a fuse that could detect its proximity to a target and detonate automatically. The concept was simple. Mount a miniature radio transmitter and receiver inside the shell's nose. The transmitter would emit radio waves continuously. When those waves reflected off a nearby aircraft, the receiver would detect the reflected signal and trigger the detonator. Simple in concept, but seemingly impossible in execution. An artillery shell fired from a 5-inch naval gun experienced acceleration forces of 20,000 times normal gravity. The shell spun at 25,000 revolutions per minute. Any electronic components inside would be subjected to crushing forces and violent rotation that would pulverize conventional vacuum tubes into powder. Every engineer who examined the problem concluded that it couldn't be solved with existing technology. Harry Diamond refused to accept that conclusion. He had spent 20 years solving problems that other people considered impossible. He understood that the key wasn't developing entirely new physics or waiting for miraculous breakthroughs. The key was systematic engineering, identifying each specific failure mode, designing solutions for each problem, testing rigorously, and iterating until every component worked reliably. He began by studying exactly what happened to vacuum tubes when subjected to extreme acceleration. He built air cannons that could fire test tubes into solid blocks of wood, simulating the forces they would experience in actual combat. He examined the shattered fragments under microscopes, identifying exactly which structural elements failed first. Then he redesigned those elements to be stronger. The glass envelopes cracked under acceleration. Diamond experimented with different glass compositions and wall thicknesses until he found combinations that could withstand the stress. The filaments broke. He tested dozens of different mounting configurations and wire types until he developed filaments that could survive 20,000 G-forces without snapping. The internal tube elements came loose and destroyed the circuits. He redesigned the mounting structure to hold every component rigidly in place, even under extreme vibration. Every single component in a proximity fuse vacuum tube had to be reconsidered and redesigned. Diamond worked with manufacturers to develop new production techniques. He tested prototype after prototype, documenting each failure and each incremental improvement. His colleagues thought he was wasting time on an impossible project. Military officers questioned whether the effort was worthwhile when conventional ammunition seemed adequate for most purposes. But Diamond had calculated the potential impact. If proximity fuses could increase the effectiveness of anti-aircraft fire even threefold, they would save hundreds of Allied aircraft and thousands of aircrew lives. If they could be adapted for ground artillery, they would multiply the lethality of every artillery shell fired, potentially shortening the war and saving tens of thousands of soldiers' lives. The mathematics were clear. This wasn't an academic exercise. This was technology that would determine whether democracies or fascist dictatorships controlled the future of human civilization. Diamond drove himself relentlessly, working 16-hour days, sleeping in his laboratory when experiments required constant monitoring, and pushing his team to maintain impossible schedules. By 1939, when Germany invaded Poland and Europe plunged into war, Harry Diamond had working prototypes of proximity fuses that could survive being fired from rockets. Rockets had relatively gentle acceleration compared to artillery shells, which meant the electronic components faced less stress. The British had reached similar conclusions in their own research programs and had developed comparable rocket-fused designs. But nobody had solved the artillery shell problem. The acceleration forces were simply too extreme. Conventional wisdom held that vacuum tube-based proximity fuses for high-velocity artillery were impossible to build. German scientists had explored the concept extensively and had concluded it couldn't be done. British researchers had achieved limited success with rockets, but had failed to adapt the technology for artillery. Harry Diamond believed otherwise. He had spent 5 years developing miniaturization and ruggedization techniques that no one else possessed. He had tested thousands of prototype components and had built up an encyclopedic understanding of exactly how much stress each element could withstand. He knew that vacuum tubes could be made small enough and strong enough to survive artillery firing. The engineering was extraordinarily difficult, but it wasn't impossible. What he needed was resources, manufacturing capacity, and time. In August 1940, a British technical mission led by Henry Tizard arrived in the United States, carrying Britain's most secret military technologies, including circuit diagrams and prototypes of their proximity fuse designs. The British hoped American industry could solve the manufacturing problems they couldn't overcome alone. The National Defense Research Committee assigned the Proximity Fuse project to Section T of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. The section was led by Dr. Merle Tuve, a physicist who had helped develop theoretical foundations for radar in the 1920s. Tuve understood that the core technical challenge wasn't the concept, but the execution. He needed someone who could bridge the gap between theoretical physics and practical engineering, someone who understood both the science and the manufacturing realities. He needed Harry Diamond. Diamond joined Section T as chief engineer in September 1940 with a clear mandate: make proximity fuses that could survive being fired from 5-inch naval guns and detonate reliably near fast-moving aircraft. He had 9 months to develop working prototypes. The Navy needed effective anti-aircraft weapons immediately. Japanese forces were advancing across the Pacific. American ships were being attacked by aircraft that conventional anti-aircraft guns couldn't hit reliably. Without better defenses, the Navy couldn't operate effectively in hostile waters. Diamond assembled a team of engineers and physicists, but he made it clear that this wouldn't be a theoretical research project. This was practical engineering under wartime pressure. They would test components to destruction, identify failure modes, redesign, and test again. They would iterate rapidly, document everything, and push toward working prototypes as fast as humanly possible. The first challenge was the vacuum tubes. Diamond brought his 5 years of miniaturization research to Section T. He worked directly with Western Electric Company and Raytheon, the 2 firms that manufactured miniature vacuum tubes for hearing aids. Hearing aid tubes were already ruggedized for portable use and manufactured at scale. Diamond's specifications called for tubes that were smaller, stronger, and more shock-resistant than anything currently in production. The manufacturers initially resisted. They didn't believe such tubes could be built. Diamond showed them his test results from the National Bureau of Standards, demonstrating that properly designed miniature tubes could survive extreme forces. He explained exactly which design modifications were necessary and why each change would improve survivability. The engineers at Western Electric and Raytheon had never worked with anyone quite like Harry Diamond. He wasn't a theoretical physicist proposing elegant solutions that couldn't be manufactured. He was a practical engineer who understood production realities and could explain exactly how to modify existing manufacturing processes to produce the components he needed. He spoke their language. He understood their constraints. And he had data demonstrating that his approach would work. The manufacturers agreed to develop prototype tubes based on Diamond's specifications. By January 1941, they had miniature vacuum tubes that survived initial testing. By June, they had tubes that could withstand 20,000 G-forces and 25,000 RPM rotation rates. The tubes were barely larger than rifle cartridges, but they worked reliably under conditions that would have destroyed conventional tubes instantly. With working vacuum tubes in hand, Diamond turned to the circuit design. Each proximity fuse required 5 miniature tubes, along with resistors, capacitors, a battery, a safety mechanism, and a detonator, all packed into a space smaller than a beer can and weighing less than 2 pounds. The circuit needed to transmit radio waves continuously, detect reflected signals, and trigger the detonator when the reflected signal strength indicated the shell was within lethal range of a target. Diamond designed a system using separate transmitter and receiver circuits instead of a combined transceiver. This simplified the electronics and made the system more reliable under combat conditions. The transmitter operated at a fixed frequency, broadcasting continuously. The receiver monitored for reflected signals. When the signal strength exceeded a predetermined threshold, indicating the shell was near a target, the circuit would close and fire the detonator. But reliable circuit operation required stable power, and that meant solving the battery problem. Standard batteries couldn't withstand firing shock. The acceleration forces would rupture the casing and spill corrosive electrolyte throughout the fuse, destroying the electronics. Diamond developed a reserve battery that remained inert during storage and handling, but activated automatically when the shell was fired. A small glass ampule containing electrolyte was mounted inside the battery casing. When the shell was fired, the setback force shattered the ampule, releasing the electrolyte and activating the battery. The system was elegant, simple, and worked perfectly. The battery remained stable for months in storage, then activated instantly when needed. Safety mechanisms required equally careful engineering. The fuse needed to remain completely inert during handling, transportation, and loading into the gun. It couldn't arm until the shell had traveled far enough from the gun to protect friendly forces from premature detonation. Diamond designed a complex system using mercury switches that required centrifugal force from the shell's rotation to close, combined with a timer that ensured at least 0.3 of a second elapsed after firing before the fuse could detonate. This meant the shell had to travel at least 750 feet from the gun before it became active. Even if a shell misfired and fell near the gun crew, it would remain harmless. The safety systems were tested exhaustively. Diamond personally supervised tests where shells were deliberately mishandled, dropped, struck with hammers, and subjected to every conceivable accident scenario. The fuses never armed prematurely. The safety mechanisms worked flawlessly. By August 1942, Section T had working proximity fuses ready for operational testing. The Navy conducted live fire tests in the Chesapeake Bay using the cruiser USS Cleveland. The test was scheduled for 2 days. It ended after 1 day because all the target drones were destroyed. Gun crews aboard Cleveland fired 4 shells. 3 drones were obliterated. Navy observers present at the test were astonished by the results. For the first time in history, anti-aircraft gunners could reliably hit moving aerial targets without direct hits. The shells just needed to pass within 70 feet of the target, and the proximity fuse would detonate automatically, shredding the target with shrapnel. Harry Diamond watched those tests from the deck of an observation vessel, and he understood that warfare had just changed forever. The farm boy, who had learned electronics by kerosene lamplight in a rural workshop, had created a weapon that would save thousands of Allied lives and help win the war against fascism. But successful testing was only the beginning. Now they needed to manufacture these devices by the millions. The transition from successful prototype to mass production revealed the true magnitude of what Harry Diamond had accomplished. Creating a single working proximity fuse in a laboratory was extraordinary engineering. Manufacturing 22 million of them, while maintaining quality control across dozens of contractors, represented something else entirely: industrial coordination on a scale that had never been attempted before. Diamond understood that his role had shifted. He was no longer just an engineer solving technical problems. He had become the keeper of knowledge that needed to be transferred to factory workers across America, most of whom had never seen electronic components before the war began. In January 1943, Section T reorganized as the Applied Physics Laboratory under Johns Hopkins University, with Merle Tuve as director and Harry Diamond as chief of the Fuse Division. The project now involved 26 contractors and 10,000 workers. More than 100 American companies contributed to proximity fuse production, including General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, Philco, and even Wurlitzer, the organ manufacturer. Each proximity fuse contained 130 miniaturized electronic components. Assembly required precision work that most factories had never performed. Diamond spent months traveling between manufacturing facilities, training quality control supervisors, troubleshooting production problems, and ensuring that every fuse met military specifications. He discovered that transferring knowledge from laboratory to factory floor was harder than solving the original engineering challenges. The workers assembling these fuses had no idea what they were building. Security was absolute. The project carried the same classification level as the Manhattan Project developing the atomic bomb. Women working assembly lines at the Crosley Corporation in Cincinnati, Ohio, inserted miniature vacuum tubes into mysterious cylindrical housings, without knowing those housings would be loaded into artillery shells. Men operating punch presses at General Electric's Christmas tree lamp factory in Cleveland manufactured components for devices whose purpose remained classified. When workers asked supervisors what these devices did, they received the same answer every time: "This work is critical to winning the war, and that's all you need to know." Diamond understood the frustration this caused, but he also understood the stakes. If German intelligence learned that American factories were producing miniature radar sets small enough to fit inside artillery shells, they would redirect enormous resources toward developing countermeasures. German scientists might discover design flaws that could be exploited. They might develop jamming techniques that could blind the fuses. They might even copy the technology and produce their own proximity fuses, which would devastate Allied bomber formations over Germany. The security restrictions weren't bureaucratic paranoia. They were essential to maintaining a technological advantage that could determine whether democracies or dictatorships controlled the post-war world. By mid-1943, American factories were producing more than 100,000 proximity fuses per week. The cost had dropped from $732 per unit in early 1942 to just $18 by 1945. That price reduction reflected both improved manufacturing efficiency and economies of scale that only American industry could achieve. But it also reflected something deeper: the ability of ordinary workers to master complex tasks when given proper training and clear standards. Diamond had designed the fuses to be manufacturable by people with minimal technical education. He had created assembly processes that broke complex tasks into simple steps. He had developed quality control procedures that caught defects before fuses left the factory. The system worked because Diamond understood that winning wars required more than brilliant engineering. It required making that engineering accessible to an entire nation. The Navy began using proximity fuses operationally in November 1942, distributing them to ships operating in the Solomon Islands. But the fuses came with strict restrictions. They could only be used over open water, where dud shells would sink to the ocean floor. If a fuse failed to detonate and fell on land, Japanese engineers might recover it and reverse engineer the technology. That risk was considered unacceptable by Pentagon officials, who feared that any compromise of the technology would hand Japan and Germany a weapon they could use against Allied forces. On January 5, 1943, the light cruiser USS Helena tested those restrictions during combat operations off Guadalcanal. Japanese dive bombers attacked after dropping their bombs, and Lieutenant Red Cochran ordered his gun crews to fire 3 salvos with proximity-fused shells at the departing aircraft. All 3 shells exploded in the air near the dive bomber. The aircraft disintegrated and fell into the ocean. Helena's crew had achieved the first confirmed combat kill using proximity-fused ammunition, and it wasn't a lucky hit. It was repeatable technology. Over the following 12 months, the effectiveness of proximity fuses in naval combat became undeniable. In 1943, Navy ships fired 9,128 proximity fused rounds and destroyed 61 enemy aircraft. That was 1 kill for every 155 shells fired. The old-time fused shells had required 508 rounds per kill. The improvement was more than threefold, and this was just the beginning. As gun crews gained experience and fire control systems improved, the kill ratios got even better. By 1944, proximity-fused shells were accounting for hundreds of aircraft destroyed across the Pacific theater. During the Battle of the Philippine Sea in June 1944, American ships equipped with proximity fuses shot down numerous Japanese aircraft, attempting to attack carrier task forces. The Japanese naval aviators, among the most experienced in their fleet, found themselves unable to penetrate defensive screens created by proximity-fused anti-aircraft fire. Harry Diamond never went to sea with the fleet, but he received regular reports from Navy ordnance officers describing the fuse's performance under combat conditions. He read accounts of kamikaze attacks stopped by proximity, fused shells detonating around suicide aircraft. He studied after-action reports detailing how ships that would have been sunk by conventional air attacks survived because proximity fuses created defensive barriers that attacking aircraft couldn't penetrate. He knew that every aircraft shot down represented crew members who would return to base, and every ship saved represented hundreds of sailors who would survive the war. The mathematics of survival were simple. His technology was keeping people alive who would otherwise have died. But Diamond also understood something that troubled him deeply. The same technology that protected Allied forces would eventually be turned against enemy soldiers with devastating effectiveness. The Pentagon's restrictions on using proximity fuses over land remained in place through 1943 and most of 1944, even as Army artillery officers pleaded for permission to use the technology against ground targets. The calculus changed when Germany began launching Von cruise missiles at London on June 12, 1944. The V-1s were jet-propelled flying bombs that flew low and fast, approaching speeds of 400 miles per hour. Traditional anti-aircraft guns could rarely hit them, because the missiles were too small and too fast for accurate time fusing. British fighter pilots tried to shoot them down or tip their wings to send them off course, but many pilots died in the attempt. The Pentagon authorized limited use of proximity fuses to defend London, initially restricting them to 90mm anti-aircraft guns positioned along the English coast where dud shells would fall into the ocean. The results were immediate and dramatic. In the first week of operations, British anti-aircraft guns destroyed 17% of incoming V-1s. By the end of the fourth week, proximity-fused shells were accounting for 79% of all V-1s destroyed by anti-aircraft fire. By late August, that percentage reached 82% on some days. The Germans launched 9,300 V-1s at England between June and August. Without proximity fuses, the casualties and destruction would have been catastrophic. British Prime Minister Winston Churchill later called the proximity fuse potent against the small unmanned aircraft and credited it with preventing far greater loss of life. Harry Diamond read Churchill's assessment and felt a profound sense of validation. The farm boy who had taught himself electronics in a rural workshop had created technology that saved London from devastation. But the most significant test of proximity-fused artillery came during the Battle of the Bulge in December 1944. At 5:30 on the morning of December 16th, Germany launched Operation Watch on the Rhine, attacking through the Ardennes forest with 3 full armies hitting thinly held American positions with overwhelming force. The attack achieved complete surprise. German armour punched through American lines and began driving west toward the Meuse River and the Belgian port of Antwerp. Colonel Oscar Alfred Axelson made the decision to use proximity fuses within minutes of the attack beginning. His 406th Field Artillery Group had just received shipments of Posit shells, the Army code name for proximity-fused artillery rounds. When the 38th Cavalry Squadron called for fire support, Axelson knew conventional shells would have limited effectiveness against German infantry advancing through forested terrain. But proximity-fused shells detonating above the trees would kill anything in the open. He ordered his gunners to load Posit and fire, violating direct orders from Supreme Command. The effect was immediate and devastating. German infantry caught in the barrage were cut down by airbursts they never saw coming. The attack on the 38th Cavalry Squadron collapsed. 3 days later, General Dwight Eisenhower formally requested authorization to use proximity-fused artillery shells across the entire European theatre. On December 21st, all restrictions were lifted. The timing was critical. American artillery battalions supporting defensive positions fired proximity fuses with devastating effect against attacking German forces. Soldiers who had felt safe in trenches and foxholes discovered that overhead cover meant nothing against shells that detonated 30 feet in the air, raining shrapnel straight down into their positions. By December 23rd, estimates suggested as many as 2,000 German soldiers had been killed by proximity-fused artillery shells in just the first few days of their use. German commanders offered rewards for any soldier who could recover an intact proximity fuse. They needed to understand how the weapon worked so they could develop countermeasures or copy the technology. In late December, German forces captured an American ammunition dump containing 20,000 proximity-fused artillery shells. German engineers examined the fuses carefully. They recognized sophisticated electronics were involved, but they couldn't understand how the technology worked. Most critically, German engineers refused to believe that miniature vacuum tubes could survive the acceleration forces of artillery gun firing. Their own research had convinced them such tubes were impossible to manufacture. They assumed the captured fuses were defective or designed for a different application. They never realized what they were looking at. On the night of December 25th and 26th, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River near Echternach, Luxembourg. American artillery units fired a concentrated barrage using proximity-fused shells. The shells detonated above the river, and the German troops massed on the banks. There was no cover on the riverbank, no place to hide. Patton wrote a letter to the War Department describing the result. "The new shell with the funny fuse is devastating. We caught a German battalion trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad you all thought of it first." 702 confirmed. German dead in a single artillery barrage. That was unprecedented lethality. Throughout the Battle of the Bulge, proximity-fused artillery devastated German formations caught in the open. Prisoners of war interviewed after capture described being in a dazed state after surviving proximity-fused barrages. They realized they were facing a new kind of artillery but couldn't understand how it worked or how to evade it. Some German soldiers simply refused to leave their bunkers when proximity-fused artillery was falling. The psychological impact was as significant as the physical casualties. Soldiers who had trained for years in defensive tactics discovered that everything they knew about surviving artillery fire was obsolete. Harry Diamond never witnessed combat firsthand, but he received detailed reports from artillery officers describing the effects of his technology on enemy forces. He read accounts of German soldiers found dead in foxholes that had protected them from conventional type artillery. He studied photographs of defensive positions that had been rendered useless by airbursts. He understood intellectually that his fuses were killing human beings, not just destroying targets. Young men were dying because he had solved engineering problems that other people considered impossible. The knowledge weighed on him. He had created this technology to save Allied lives, and by every measurable standard he had succeeded beyond anyone's expectations. But success in warfare meant death for the enemy, and Diamond struggled with the moral complexity of that reality. In the Pacific Theatre, proximity fuses had an even more dramatic impact against kamikaze attacks. By 1945, Japanese forces had adopted suicide tactics, using aircraft loaded with explosives to crash into American ships. These attacks were extremely difficult to defend against because conventional anti-aircraft fire required direct hits on aircraft that were deliberately trying to crash into ships at close range. But proximity-fused shells created defensive barriers around ships that were almost impossible for kamikaze aircraft to penetrate. Navy studies showed that ships using proximity-fused ammunition were 5 to 10 times more effective at stopping kamikaze attacks than ships using conventional time-fused shells. In the 7 months from January to July 1945, American ships expended nearly 2/3 of all proximity fuses used during the entire war, shooting down more than 200 aircraft and preventing catastrophic damage to the fleet. The effectiveness went beyond statistics. Japanese pilots knew that approaching American ships equipped with proximity-fused anti-aircraft guns meant flying into an invisible sphere of death. There was no way to evade this defense through skill or courage. The psychological impact on enemy forces was profound, contributing to the sense of hopelessness that pervaded Japanese military planning in the final months of the war. After Japan surrendered in August 1945, the proximity fuse project was declassified, and the full scope of the achievement became public. Dr. Merle Tuve received recognition for leading the applied physics laboratory during the war. He was awarded the Presidential Medal for Merit by President Harry Truman and named an honorary commander of the Order of the British Empire. But Harry Diamond received relatively little public attention, despite being the chief engineer who had solved the core technical challenges that made mass production possible. Diamond returned to the National Bureau of Standards after the war and continued working on military electronics research. He developed radio proximity fuses for guided missiles, improved radar systems, and contributed to early computer development. He held more than 100 patents by the time he retired, but he rarely spoke about his wartime work on proximity fuses. When asked about the project, he emphasized the collaborative nature of the effort and the contributions of factory workers who had manufactured millions of fuses without knowing what they were building. He seemed uncomfortable with praise, perhaps because he understood that his greatest achievement had been creating technology designed to kill human beings more efficiently. Harry Diamond died on June 16, 1948, at the age of 52, from a heart attack. His obituaries mentioned his contributions to military electronics and his leadership role in proximity fuse development, but most did not detail the specific engineering problems he had solved. The technology had been declassified for 3 years, but it remained obscure outside military and technical circles. Diamond himself had never sought publicity for his wartime work. He believed that engineering achievement should be measured by results, not recognition. The proximity fuse had saved Allied lives and helped win the war. That was what mattered to him. The workers who assembled proximity fuses in factories across America went back to their peacetime jobs when the war ended. Most never learned exactly what they had been building. The soldiers and sailors who benefited from proximity-fused ammunition rarely knew the technical details of how the fuses worked. They just knew that anti-aircraft guns were suddenly much more effective and artillery barrages were far more lethal. The technology remained mysterious, even to the people whose lives it saved. The 702 German soldiers killed by proximity-fused artillery on the banks of the Sauer River in December 1944 were buried in military cemeteries in Luxembourg and Germany. Their graves do not mention how they died. Military records list them as killed in action by artillery fire, which was true but incomplete. They were among the first ground troops anywhere to be killed by technology that their own scientists had declared impossible to build. The story of Harry, Diamond and the proximity fuse is ultimately a story about the power of persistence over perceived limitations. Diamond succeeded where others failed, not because he possessed superior theoretical knowledge, but because he refused to accept conventional wisdom about what was possible. He understood that engineering challenges that seemed insurmountable could be broken down into smaller problems, each of which could be solved through systematic experimentation and incremental improvement. He demonstrated that formal education and prestigious credentials mattered less than practical knowledge and relentless determination. And he proved that one person with clarity of purpose and freedom to pursue unconventional approaches could change the course of history. The proximity fuse saved thousands of Allied lives during World War II. It protected cities from drone attacks. It defended ships from kamikaze strikes. It multiplied the effectiveness of artillery fire and helped shorten the war in Europe. But perhaps more importantly, it demonstrated that technological advantage in warfare comes not from brilliant individuals working in isolation, but from systematic collaboration between researchers, engineers, manufacturers, and military personnel. Diamond created the core technology, but 22 million proximity fuses were produced only because thousands of people at hundreds of companies contributed their skills to solving manufacturing challenges that were just as difficult as the original engineering problems. This is how wars are actually won, not through dramatic breakthroughs or lone geniuses, but through the coordinated effort of ordinary people doing extraordinary work under impossible pressure. The farm boy who learned electronics by kerosene lamplight became the engineer who revolutionized anti-aircraft defense because he never stopped believing that impossible problems were just difficult problems that nobody had solved. Yet, his legacy lives on in every piece of military technology that seems impossible until someone builds it anyway. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.